And on the count of 3. 1, 2. Wait, we'll take a minute. Okay. 1, 2, 3. Say it. 59. 59 chorus. All right. Oh, this is a great question. You'll love this one. I don't like you anymore, Mr. Seamon. I don't like you at all. Okay, so it says this. Is there a number A such that the limit as x goes to -2 exists? So here's the thing. What kind of function is this? What kind of function is it? It's a rational function, right? Correct. And they're on rational functions. What are the two things that can happen on rational functions that are kind of different, and the only places you've really seen them are on rational functions? They could have what? They could have a removable discontinuity.
No.
Yeah, exactly. No, that's exactly it. And asymptotes. Absolutely. Now here's the thing. Does the limit exist at the x value of a vertical asymptote? No. Exactly, right. Well, technically, I guess you could say it could go to infinity, right? You know, if both sides, if you had a vertical asymptote, we've said this, if this is x is equal to -2, we could say maybe it goes to infinity there, or goes down, it will go to negative infinity. We're going to try to avoid that. Instead, which one are we going to aim to try to create? A removable discontinuity. Here's the thing. Can we plug in -2 into this rational function?
No.
No, because if you plug it in, what happens? What's the problem?
You get 0 in the denominator.
Don't like that, right? So we want to remove that. So before we do anything, what would be one great thing to do to this equation? What would be one great thing? Factor it, exactly. Specifically factor the denominator. So we're really looking at this. The limit as x goes to -2 of x plus 2 times x minus 1. That, yes. Correct. Got it, right? We want to make it so there is a what at what. We want to make it so, I know that was vague. There is a what? There is a RD at x equals
-2.
Exactly. So when we say removable discontinuity at x equals -2, what do we want to cancel out?
The x plus 2.
And an x plus 2 at the top. Correct?
Yeah.
So if x plus 2 is going to be on the top, it needs to be a what of 3x squared plus ax plus a plus 3? A factor, right. So what are we looking for? We want to make x plus 2 times something is equal to 3x squared plus a plus 3, right? So question mark is equal to 3x squared plus ax plus a plus 3 over what? X plus 2, not question mark. Thank you. Corey, here you go. Like that, right? That's what we want to figure out. Okay, what are we going to do to this? Yeah. Because if there is a removable discontinuity there, the limit still exists. If you're traveling along and there's a hole right here at x equals -2, does the limit exist at x equals -2? Yes. Right now, we cannot plug in -2 into this rational function because the denominator would be 0. So we want to make it so that you can. So what are we doing? We're changing the function by only doing one thing. We're putting a dot where? At that removable discontinuity. But we have to figure out what the a value is going to be so that we're guaranteed to have a removable discontinuity. So how do we do that? Well, we're looking at this right here. We're looking at this. We need to rewrite this. How do we go about rewriting that? You have two methods of rewriting that. You've done them both. You all have experience doing both.
Multiply by...
No, we're not multiplying by anything.
Okay.
You've learned two things you can do to divide polynomials. What? Synthetic division is absolutely the one I would like you to do. If you're dividing by x plus 2, what number are you running through synthetic division?
-2.
-2. And what are the coefficients of this quadratic in the numerator?
3a, and 3.
Close. You're really close. 3 and a are coefficients. And what's the last? A plus 3 is the constant, right? That's the trick to this. So what do you do first in polynomial synthetic division? You drop down the multiply by, add them together, multiply by. So you get -2a plus. We add them together, and what do you get? Plus 15, right? This is supposed to be a factor, meaning it divides evenly, divides out, right? So what should the remainder be?
0.
So what does A equal?
15.
15. Done. Let's check to see if this how would we check to see if this works? What should we do with the 15? Plug it in, yeah. We take it here, and let's see what the factorization becomes. Let's just check it. So it would be 3x squared plus 15x plus 15 plus 3. So that's 3x squared plus 15x plus. What do we factor out first?
3.
3. X squared plus 5x plus 6. What does this factor into? 3 times x plus 2 times x plus 3. So that's the numerator. So our new limit is this. The limit as x goes to 3 over x plus 2 times, well, I just said one thing and wrote another, all over x plus 2 times. We just chose an a value that turned it into that, right? By choosing that a value, what can you do? Cancel out that. Therefore, the limit does exist. What is the limit going to be? 3 times negative 2 plus 3 over negative 2 minus 1, which that's going to be, it's going to be 1 over what? So our limit is negative 3. So does the limit exist? Yes, we chose an a value accordingly, we found a limit. Is that necessarily the only answer to this question? No, this is the one that I would hope you would aim for. This creates a removable discontinuity at x equals negative 2. The limit does exist at a removable at the x value of a removable discontinuity. Does that make sense? This is a little tricky because you have to remember some pre-calculus and algebra 2 stuff. Use the graph to estimate the value of the limit as x goes to 0. So, did you use your graph?
Yeah.
Yeah, I'll do this. So record again. So what's a good zoom to do here?
Box. Or
Or you
in.
can just do
Yeah.
For some reason this is not good. So zoom box. You can do zoom in. I like doing zoom box because it allows me to zoom in real far. I actually don't know what the how it goes about choosing what zoom in is going to be. So it looks like goes. So it's not quite a vertical line. So what does it look like it's going to be? So if you're just estimating, you could use trace. What does it look like the y value is?
2.28.
0.28, yeah. And does our graph agree? Yeah. It looks like by our graph, we estimate it to be about this point right here. So we estimate the limit to be about 0.2887 is what this trace gave us. Use the table of values to estimate the limit to 4 decimal places. So if we're going to use if we're going to use the table, we have to do table set first. So where should we start? If we're looking around 0, where should we start? Negative what?
Negative 0.5.
0.5?
Yeah.
Okay, we can do negative 0.5. What do you want the step to be? Let's do 0.01. Let's do 0.01 because we want to get close. And remember, close is relative. We can always get closer. So let's use the table. See what the table looks like now. You know, we can keep on clicking here. I mean, I just like seeing what the path looks like here. We're getting there, right? We're getting there. What happens when we get to 0?
Error.
Why is there an error?
Because it can't do it.
Why can't it do it?
Because it's divided by 0.
What doesn't exist? Because at 0, the equation is dividing by 0. Now, here's the thing. If you look at this limit, on both sides, does it look like it's approaching the same thing?
Yeah.
Yeah, it looks like from both sides it's approaching the same thing. From the right and from the left, it looks like it's going to about the same. If we're going to estimate this, 0.288 what?
6.
Yeah, between 9 and 4, 13, about 288.6-ish or 6 or 7. It's hard. Could we get a better estimate if we set a different table set?
Yeah.
Yeah, absolutely.
Well,
you
if you
could.
go too far, it tells you it's 0.
Well, yeah, because what it's doing is the calculator is fundamentally rounding at a certain level. You're absolutely right. So let's table set this. Let's do second table set. Let's start it at, how about negative 0.01?
Window.
Oh, yeah, I'm sorry. Second table set, negative 0.01. And let's make the step negative 0.001, like this. And let's do the table and see what it says.
You're going
In the wrong direction. I'm
You
sorry.
put the steps to be negative.
Oh, I did. Did I put the
Yeah,
step
you
negative?
did.
So I just need to go press the up button. Okay. I know. I really got to stop this clicking thing. I'm not very good with the mouse. And I missed it again! Okay, here we go. So that's actually not bad. Cool. So could you get arbitrarily, well, not arbitrarily close, because we've as Hutch pointed out, if you get too close, it kind of fizzles out and it starts rounding. But it looks like it's 0.288675 or something like that, right? 66? 2866 maybe? Okay. So the next part of the question asks, that was part,
A and B.
use the limit laws to find the exact values of the limit. So basically this is how do we actually find the limit?
Yeah.
That's what it's asking. Okay, so let's write this down, and we get to learn a new maneuver. So I'll pause this and get us started. Our clue that we have a nice place to go is that look at the graph. Is there an asymptote here?
No.
It doesn't look like it. It looks like it's a removable discontinuity. So theoretically, if it's a removable discontinuity, there's a factor in the numerator that cancels with a factor in the...
Denominator.
So theoretically, it looks like there's a way to factor out what?
X.
X. So let's multiply this out and see what happens. We do this, and we end up with 3 plus x plus root 3 times root 3 plus x, right? Minus root 3 times, this one now is the same thing, right? But it's negative. Minus what?
3.
Over x times this thing, right? Are we okay with that algebra right there?
Yeah.
All I did was distribute. What cancels?
The middle two.
Yeah, it's the two middle terms. Boom and boom. So what are we left with? We're now left with this limit. The limit as x goes to what?
0.
0 of 3 plus x minus 3 over x times 3 plus x plus root 3, right? What cancels in the numerator?
The X.
The 3's, right? And then what cancels now? Now what cancels?
The X's.
The x's. So now what are you left with?
1 over.
Limit as x goes to 0 of 1 over, the 1 is important, everybody, root 3 plus x plus root 3, right? What's cool about this?
You can do anything you want and it won't affect
What can you
the
do?
numerator.
You can plug 0 in now. This is equal to 1 over root 3 plus root 3, which is equal to 1 over 2 root 3. You are allowed to leave the answer like that. If you wanted to rationalize that, that would equal root 3 over 6. Root 3 over 6. What is root 3 over 6? Does that match what we got?
Yeah.
Absolutely. So basically what did we do? Did we factor out x? Essentially. We essentially proved you could. So does that match what we got? Yeah, it does. It absolutely does. So what was this new maneuver we learned? We'll just call it this, rationalize. Ish. We still end up with a radical in the denominator, but what did we do? We rationalized so that we could now cancel the problem term, right? And because we canceled out the problem term in the... Well, we actually canceled from the... But the more important, we got it out of the denominator. Because we got the problem term out of the denominator, which the problem term was there because... We called it problem because it created a 0 in the denominator. It's gone. And now what can we do? Now we can evaluate. Cool, huh?
Yeah.
You like that?
Can you go up?